exponential and logarithmic graphing. So what I've got at the top of the screen is two particular examples of what these graphs look like. First of all, let's just take the original function e to the x. E to the x is an exponential graph. It goes through 1 because anything to the power of 0 is 1, and it has an asymptote at y equals 0. Now, what we can see is the fact that, and what we should hopefully know, is the fact that there is an inverse relationship between these two graphs. The log base e graph is reflected in the y equals x line because it's an inverse. And so therefore the asymptote will flip to x equals 0. The point that was originally 0, 1 is now going to be 1, 0, and it's going to flip to the other side. It looks like so. Similarly, if we have a look at this graph here, our original graph is f of x equals 6 to the power of x. Our inverse is the logarithmic graph, log base 6 of x, g of x. The asymptotes will change and the graph will flip and reverse. So let's have a look at some examples. We want to sketch this graph. So what we can do is we can work on this in terms of our transformations, and then we might have to delve a bit deeper. So what we can see straight away is the fact that in this case, we have a situation where this x plus 2 tells us that the whole graph moves 2 to the left. We also know that this plus 1 tells us our graph moves up 1. Now, bearing in mind that we had the original particular piece of information when we have a normal log base e graph, we normally have the log base e graph does this. It goes through 1, and we know something to do with the asymptote. We know that the asymptote is at x equals 0. So if that's the case, then if we move 2 to the left, the whole graph is going to move to the left 2. It's also going to move up 1. Now that's okay for us in terms of this instance, but the only thing it really helps us to do is it helps us to put fairly accurately on this unscaled graph that x is equal to minus 2 is an asymptote. What it does with this point here, this 1, 0, means that we move 2 to the left, which puts us at minus 1, and it tells us to move 1 up. So we know for a while there's going to be a point up here somewhere that's going to be minus 1, 1. But apart from that, we don't actually know much about this. So we know our graph is going to look something like this, with our points minus 1, 1 around about there. And what we need to do is need to work out where the intercepts are. So just like normal, if we want to work out our intercepts, if we want to work out the y-intercepts, we need to say at x equals 0. And we're just going to work out what we're left with. Log base e of 2 plus 1. Now if we're trying to do this without a calculator, we're not going to get a decimal answer. We're going to actually just leave it log base e of 2 plus 1. If we're looking for an exact value, if we're looking for a value where we've got to work it out and have it as a decimal, we put that into our calculator and we'll get a particular answer. To get our x-intercepts, we're going to work on it in a slightly different principle. We're going to work with y equals 0, and we then end up with 0 is equal to log base e of x plus 2 plus 1. And we get to minus 1, log base e of x plus 2. And the opposite of log base e is then when we make it e to the power of negative 1. Now that might strike us as being incorrect because the fact that it looks a bit of a strange one. But remember the fact that e to the power of minus 1, all that means is it's 1 over e. E to the power of 1 is around about 2.7, so it's still a feasible number. And so if we're then going to be writing this as a tech-free answer, we're going to write it as that particular number. And when we write it on our answer here, we're going to make it a little bit clearer for us. We're going to write it in terms of a positive power, just to make sure. And that's how we do that one. Let's think about this next one. Example 2, f of x is equal to 2 log base 10 of 3x. So let's think about what this does. We can again work out what's going on with our particular graph in terms of transformations, or we can just work out the intercepts and go from there. What we should hopefully be able to do is, if we start with our original equation of log base 10 of x, what we can see is the fact that then what happens is it now becomes log base 10 of 3x with a 2 in front. So thinking about our transformations, what this is going to do is our xy value is now going to become x over 3 and 2y. And for those people who follow the transformations, we're going to be saying that if we make this equal to this, we're going to get ourselves as a mapping notation as that. So we're going to have x equal to 3x dash, so our x dash is equal to x on 3. For those people who don't like necessarily doing it with a function notation. So what does that mean? Well, think about our log base 10 graph. Our log base 10 graph will normally have same situation as last time. We'll have an asymptote, and it'll still be on the same points. Everything will be exactly the same as it normally is, the same shape. So what we're going to be doing now is the fact of we're going to be sitting there thinking, well, the only things that change, obviously, the points and the asymptotes. If we put our asymptote of x equals 0 into here, 0 divided by 3 is still 0. So the asymptote will stay exactly the same as what it was last time. Which means our graph is going to look very similar to what it was last time. However, we've now got to work out this particular point. So if you have a look at this, there's actually not any particular y-intercept, is there? If you think about this in terms of mathematically, a y-intercept is when x equals 0. And if you sit there and think about the fact of when you try and put log base 10 of 0, it doesn't work. Similar to here, we know that any log base graph doesn't have a y-intercept because of that asymptote there. So the y-intercept we don't need to worry about. Our x-intercept though, we do need to worry about. And what we need to do there is we're going to make it equal to 0, should I say. We're still going to have log base 10. And remember, to undo this, we're going to go 10 to the power of 0 is equal to 3x. Remember, what's anything to the power of 0? That's equal to 1. So x is equal to 1/3. So that value there is 1/3. And that is our graph. Here. Now this looks a bit more complicated, but we can actually shorten it down a little bit based on what we already know about log graphs. So we already know that this part of the graph here which is hopefully going to update soon. There you go. 1 minus x has to be greater than 0. So we know that because of the fact that from our previous work in terms of our log base e graph is the fact that there's normally an asymptote where x is 0. So that bit can't be 0, otherwise the graph won't exist and it will be an asymptote. So if we rearrange this, what we're going to actually work out is the fact that x must be less than 1. So that puts our asymptote straight away at x equals 1. It also means that our graph, instead of it being on the right hand side this time, so it's not going to be doing something like this, it's actually going to be doing something like this or something like this. It's going to be left side, so it's always going to be less than 1. That's the best thing for us in this particular instance. Now, what we can do is we can sit there and think, okay, well, we can try and work our intercepts and see whether that gives us a general indication of whether our graph is going and curving upwards or whether it's going the opposite way. Okay, we can work at it two ways. So we've just proven that bit over there. So again, if we think of our y-intercept, our y-intercept x equals 0. If we substitute all that in, we get f of x, or should we say in this case y, to work out our y-intercept, is equal to 2 minus 3 log base e of 1. And we know the log base e of 1 from our graph at the top here. So this one here, log base e of 1 is actually 0. So when we start looking at all this information that we've got here, all this bit's going to become just a nice simple 2. So our point is going to be at 2. And then when we sit there and think about our other intercept, let's make it equal to 0 for the y value. We're now going to go 0 is equal to 2 minus 3 log base e of 1 minus x. If we rearrange all this, we get that line there. Just going to scroll up. We divide by minus 3, we actually get our answer of 2/3. And then we take the exponential and we rearrange. And that's our actual value for our x value in terms of an exponential and an exact value. So the question is now is what does that actually mean? In terms of our value, the question is, does it sit this side or does it sit the other side? And what that actually does is we can look back at this original graph and gives us a bit more of an indication. It's either going to be in position 1 or position A, or it's going to be in position B, and that gives us a general indication of what this graph's going to be. But if we go back to where our graph is and our equation is over here, you'll notice that we've already dealt with the idea that there's a few reflections. We dealt with the idea because remember we said that x is less than 1 and it has to be left of that asymptote there. So all we've got to do now is we know for a while our graph is going to do one of two things. It's either going to look something like this, or let me just put this one in there as well, or it's going to look something like that. And they're the two options that we have in this particular case. Okay, so think about what this means. Which one has given us our reflection? Well, we've got this bit here. If I was to just ignore for the time being this 2, then what we've got is we've got a minus reflection on there and a reflection on the minus 3. If we think about that in terms of the way that our graph works, then this minus 3, this bit here, would actually change our values from xy to now x minus 3y. And that would flip our values, our y values, and that would reflect them in the x-axis. So what that does is it flips it in the x-axis. So if we think about what's going on, we end up with a graph that's going through the point A instead, and it will actually end up looking something like that. So our value, 1 minus e to the 2/3. I'm just going to take out my 2, and we're just going to take out that point B, and we end up with our graph looking like that, which means it doesn't take into consideration that stage. So therefore, you have that particular example there of how to plot our graph.